Alright, silly people, here's the situation. We're going to be considering the operator q equals d squared over d phi squared, where phi is the azimuthal angle, which we're going to use the fact that it only has a range of 0 to 2 pi, right? Um, and first of all, we need to check if it's Hermitian or not. Um, and if you watched the past couple of videos, you probably guessed that it is, but we're going to go ahead and prove it. So um, what we need to prove is this situation here, where the inner product of f with qg is equal to qf with g. If you wanted to write this in the integral notation, though, you would write it as the integral dx of the complex conjugate of f times d squared d phi squared acting on g, where g and and I should say that both g and f are functions of phi, and we're actually integrating over phi. Okay, so this can be rewritten obviously as d squared g d phi squared instead. And we're going to do integration by parts on this guy by choosing u equals f star. And if we take the derivative of that, we would get df star d phi. dv you choose to be d squared g d phi squared, and so v will just be d g d phi, and there should be a d phi here as well. And so plugging that into the expression, the value of the integral becomes just uv, so f star dg d phi evaluated from 0 to 2 pi, which does go to 0 by the fact that f and g both have to be normalizable functions. And so then minus the integral v du, which is going to be now d phi df star, df star d phi dg d phi. Alright, then we have to do integration by parts on it again. So second integration by parts, we're going to choose u equals df star d phi, and then the derivative of that will be d squared f star d phi squared d phi. Then dv you would choose to be dg d phi, and then v from that would be clearly just g. So this integral here would equal minus uv, so df star d phi g evaluated from 0 to 2 pi, which again is 0 for the conditions of the azimuthal functions to be met, with a minus sign on it, and then plus the integral of v du, which this time is d phi d squared f star d phi squared g, which is how you would write in integral notation just qf with g, the inner product. So it does turn out that it is Hermitian, which was a predictable but nice result. Then we're going to find out what the eigenfunctions and eigenvalues of this operator is. So if we were to act d squared d phi squared on a function f of phi and expect back just the same function multiplied by a constant, that's the eigenvalue equation, by the way, then f of phi would have to have a pretty general form. I'm going to say that it's f phi equals some constant as possible. It could just be 1 times an exponential with plus or minus the square root of q up in the exponential argument times phi. And I'll show you why this works. If you take the first derivative of f of phi, you would get the square root of q plus or minus that times a e to the plus or minus root q phi. And then if you take the second derivative of it, right, you would get plus or minus square root of q all squared times a e to the plus or minus square root q phi. Now, of course, the square of the square root is just the thing inside the argument. And then the square of either plus 1 or minus 1 is both equal to 1. So this becomes qa e plus or minus square root q phi. So it satisfies the eigenvalue eigenfunction equation. So the eigenvalues of it are just whatever constant you happen to put inside the square root, obviously. So the eigenfunction is this, and then the eigenvalue is what's in the square root. I'll write that down. Eigenfunction, and then eigenvalue. Cool. And then finally, what is the spectrum of Q? And that is just kind of saying what values can Q actually be. And to find these, we have to make use of the fact that in functions of phi, the value for it at 0 and the value of it at 2 pi have to be the same because it has to be a cyclic function, right? So making use of that, the left side would be a e to the 0, so it's just a, while the right side would be a e to the plus or minus square root q times 2 pi. The a's would get canceled out if we just did algebra on this. And so 1 would have to be equal to e to the plus or minus 2 pi root q. And so the exponential thing, e to the whatever, only equals 1 if it has 2 pi attached. If the square root of q happens to be I, the square root of minus 1, times n, where n is an integer, right? That would be, the function would just be going around in a circle, right? Which means that, and that's also, it's plus or minus in because of the plus or minus inherent in the eigenfunction, which means if you square that, the only values that you could have for q are, well, it would be just n squared, right? Or plus or minus n squared, considering the plus or minus there. Which means that the entire spectrum of q is square integers. So you would say that q is an element of a set containing just square integers, where n is integer. Right. What does that mean for the degeneracy of the operator? It does mean that it is degenerate because you could have a integer, say 2, the number 2, and it would end up being an eigenvalue for both the plus case and the minus case. Either of those could be an eigenvalue of a plus function or a minus function, which means it is doubly degenerate because any given eigenvalue could have 2 different eigenfunctions attached to it, which is kind of wacky. So yeah, that should do it.